All right. On Thursday, Friday, and Monday, we worked on refraction, and we used this handout, which has a lot of information, but we need to pare it down a little bit. So instead of going nuts about the first page here, what I really want to stress is this second page here, particularly this picture. And if you take a look at this, there are a couple things that can happen when light changes from one medium to another, okay? Now in this case, we have air. Whoa, hey, that's very thick. Let's not use that. We have air on the outside of this glass, right? And we have water on the inside of the glass. And what we say that these things are medium or media, right? They're what light passes through. And so we're going to keep on using that word. And so you need to know what a medium is, right? It's whatever light is passing through. And the important things about that is that light travels at different speeds in different media. So it controls the speed of light. Okay, so in this case, water is going to be a slower medium. It's denser and it's slower. Not the water, but the light, right? And air is less dense, right? Oops. And it's faster. So that is what we've got here. So we've got a faster medium and a slower medium. Now when it hits it, two things can happen. You can get reflection, right? And you can get refraction. And you're going to see that we always measure the angles of either reflection or refraction from this thing called a normal line. And normal doesn't mean like ordinary. This is called the normal line because it's perpendicular, right? And that's a word that I've never heard anybody use except a math person or a science person. So unfortunately, it's not like I can say, oh yeah, you've seen this before in another situation. But normal means perpendicular. And so it's perpendicular to the surface between the two media. Okay, so normal means perpendicular. So let's look at these angles. If you even look at it quickly, you'll see that this angle here, which I'm going to call the angle of incidence, right? The angle of incidence, right, is the same as the angle of reflection. So when something reflects, let's try again, right? It reflects at the same angle that it hits at. And that you kind of probably suspected from just like playing pool or throwing a ball against a wall or whatever you have, right? That the angle of incidence equals the angle of reflection. And that's always going to be true. And we'll demonstrate that later, right? But then we also have this angle here, right? This angle here, which I'm going to call the angle of refraction. And refraction, right, is what happens when light bends into a medium. Okay, and so we're going to focus on these three angles in this exercise. Now, you might look at this and say, how does refraction even occur? Okay, and there we could actually look at this, and I will do. Let's see if I can figure out how to find it. Whoa, let's try this. There we go. If we were to look at notes that say maybe cover this same thing, right, we would find that, well, this looks like notes. Here we go. Refraction happens when light changes from one medium to another. Okay. Now, if you look at this, it's hard to figure out why this is happening, right? You know, why would the light suddenly change direction? Okay. Well, if I go back to Cami for a second, maybe I can draw on it. Yeah. No. So, wait, maybe I can do that. Plus. Let's add one more page, see what happens. Okay. Nice. Here it is. Right? And so what I can do is let's take a look at something like this. If we have, oops, let's suppose we have a change in medium like this. So we have water here, right? And we have air here. But instead of using light, we're going to use a car. Okay? So we're going to have a car driving in like this. And we'll say that the car has wheels because it's a car, right? So like back wheel, we'll make it kind of parallelish. We'll draw our box of our car, right? It's going to be a really wide car, it seems. Because, I don't know, because I made it that way. And so here's our car, and it's got front wheels, right? And we'll even give you a windshield so the person can see out. And I guess, let's see, driver's on the left. So here's our driver, right? And here's the back wheel, back windshield, sorry. And tailpipe maybe, a little pollution, right? So anyway, so the car's driving along, right? Now, the left wheel, or this wheel, the front right wheel, will hit the water first, and it's going to slow down. So when it gets to this point, right, you're going to have two different speeds. You're going to have V fast, right, but you're also going to have this speed, which is V slow. And what's going to happen is that the car has to turn because it's covering less distance, right? It's covering less distance as the car slows down on the right than it does where the car is going in the normal speed on the left. And so now the car is going to bend into the medium. And so it's going to go drive in like this. Right? And so you're going to have this turning of the car as it hits this new medium. Okay? And the same thing happens with light. As it changes medium, it changes speed and it causes it to turn. And we're going to measure this angle. We're going to keep on measuring these angles from this normal line. So we'll measure like this angle as the angle of incidence, and we'll measure this angle as the angle of refraction. But the whole thing is based on this change in speed because one part of it is moving fast while the other part is moving slow. Right? A change in medium causes something that is incident to change direction. Okay, so that's what we're going to use. All right, so let's go back to this then. So we've got all this junk here, and that's a lot of words. Okay, but we're going to work through it and we're going to test things so we can see what this makes sense. And so if you look at this, we're going to go to this simulation, which I have over here, and we're going to look at the two, we're going to start it up. And we've got two media here, and you can see that one medium is air and the other medium is water. I can turn the laser on, and you see that I get the laser beam, I get the refracted beam into the water, and the reflected beam out of the water. Okay? Now, if I want to measure things, I can bring this protractor over, and you can see that it has 0 up at the tippy top. And the reason it has 0 at the tippy top and the bottom is because this dotted line is our normal line. Right? So if I take a look at this thing, I can, let's try this. Maybe this will work. So let's cut this for a second. And I feel like that should have done something. Let's try again. There we go. And let's put this over here in a Photoshop document. So let's get rid of this and we'll make a new window. And here's that guy. Wow, that's very small. So let's make it bigger so we can write on it. And then we can write on it and we can say, okay, here is our angle of incidence, right? So this is theta I, right? It's our angle of incidence, right? But we then have two other angles, and this one is the one we're going to deal with mostly, and we're going to call it theta R. Okay, it's the angle of refraction. So this is refraction. Oops, nice. Okay, and that, but we also have this angle here, and this would be the angle of reflection. Maybe that's not as easy to read as I thought. Let's try to make that neater. So this is the angle of reflection. Okay, and so we have these three angles. Okay, we're going to focus first on reflection, but I want to point out that this is air and this is water, and so we're going from more dense to less dense, right? So the important things that we're going to focus on, that this is more dense. Sorry, I say more dense to less dense. We're going from less dense to more dense. This is less dense, right? Which means that light travels faster. Okay, and so it just, as we're doing this, you just need to really keep track of which medium is less dense, which medium is faster, right? Right, that means that water is more dense, and so light travels slower. Okay, so that's going to be the key thing here. All right, so we've got, this is everything that you need to know in terms of identifying the pieces parts of our work. And then I guess the only other thing that we probably need to be sure that we know is that this is the normal line. Okay, so the normal line is this guy here. Let's make it, I don't know, red. And so our normal line is this guy here, right? It's not part of the light, it's just where we're measuring our angles from. Always this, okay? So good stuff. Let's then go back to our simulation and see what we can do with it. So this is the first thing, and if you look at it, the angle starts out at 45 degrees. So this is 10, 20, 30, 40, and then 45 degrees. So if I look at my incident angle, my incident angle is 45 degrees down here. My reflected angle, if I look at this, right, now I can measure here. It's 10, 20, 30, 45. So it's also 45 degrees. And so I'll type in 45 degrees here with my magic typing tool. Let's see, type 45 degrees, right? Great. Now the two mediums, right, if you'll recall, the two media are air, right, is a medium. And let's make this a little bigger so you can see air and water, right? So we have air and water. What two things does the light do when it hits the surface? We already said that. One thing it does is reflect, and we're going to focus on reflection first. But the other thing it does is it refracts, it bends into the medium, right? And so now we've got all of this. Now we can change this angle and measure more angles of incidence and more angles of reflection. And so we're going to do that. Let's just actually do it systematically. Let's take it back to like 20 degrees. If you look at here, here is 20 degrees, 10, 20. The reflected angle is 10, 20. So it's the same. So we go back here and we get 20 degrees for the incident angle and 20 degrees for the reflected angle. One of these days I'm going to say it correctly the first time. If I bring this over to 40 degrees, here's 40, oops, here's 40, right? 10, 20, 30, 40, 10, 20, 30, 40. So it's the same again. So we can see that it seems to be with our 3 pieces of data, it seems to be the same every time. But let's check it one more time, and we'll put it down past 45. We'll take it to 60, and you can see pretty clearly that it reflects again at 60. Now you can draw a conclusion from this that these are all equal, and the way we're just going to say this is we're going to say that the angle of incidence equals the angle of reflection. And this is always true for reflected light. Okay, the angle of incidence equals the angle of reflection. Okay, and so, yay. However, let's actually deal with refraction, right? And if we look at refraction, we can play with this systematically, right? For example, if I go back to my 45-degree angle over here, you can see although reflection is at 45 degrees, refraction is something bigger than 30 and less than 35, so like 33 degrees or 32.5 degrees, right? And so if I put that in there, I would say that if we're at 45 degrees, right, I would get something like 32.5 degrees, right, somewhere like that. And so that's very different. And so we're going to look at this. Now, what if I go to 0 degrees? What can it change to? Well, I don't know. Let's see. If I go to 0, it's actually at 0. So it doesn't change if it goes straight in, and that kind of makes sense because there's no left side, right side anymore. It's perpendicular, and so there's no difference in speed from one angle to the other, right? From one side to the other. But let's change it over to like 20 degrees for a second, and you can see that it's around 15 degrees for the, right, because this is 10, 20, this is 10, 15, right, because 20 is over here. So if we put that in here, we can see that at 20 degrees, right, this is 15 degrees. Right, so that's pretty sweet. And then we can put in a steeper angle than 45, and so we'll put in 60 degrees, and you can see that it only goes up to about 40 degrees, right? So 60 degrees here gives us 40 degrees here, even though it's still 60 up here. So 60 degrees, right, gives us 40 degrees. And if we do it one more time, let's make it to 80 degrees. We'll really exaggerate it. So 80 degrees here gives us whatever this is, 30, 40, right? This is 50 up here, so that's 45, and this looks like 48 degrees. Okay, so 48 degrees. And you realize that you really have to be careful counting with these protractors because not every angle is labeled. So so we say 48 degrees. Pretty sure it's in. Okay. So you notice that it's not, they're not equal. And in fact, it starts out at 0. It starts out being equal. But then it quickly changes, right? And the bigger the angle, the bigger the difference between the refraction and the incidence, right? But you notice that these are all bigger. So we can say that the angle of incidence is always going to be greater than the angle of refraction. Well, we can say that, but this is important. It's like we're going to say when going from less dense to more dense. Okay, and that's an important idea, that we're saying that we're only making this assertion, right, when we're going from less dense to more dense, right, because we haven't tried it the other direction. Okay, so that means that if we're traveling from, and let's put it in here, we're going from less dense to more dense, right, then we can see that the angle gets smaller. And another way of saying that the angle gets smaller is we can say that we are going towards, right, the normal line, right? So a smaller angle on the refracted side means that we're getting closer to that normal line. And if we look over here, you can see that this is very far from the normal line on the incident side, but we're fairly close to the normal line on the refracted side. Okay, so we get closer to the normal line. Another way of saying is that it always bends into the denser medium. Okay. All right, good. So let's take a look at the other direction. So now we're going to switch the media. And to do that, we're going to simply say, take this and let's make it glass. Okay. Now you can see that we are in a denser medium. And the way we know that we're in a denser medium is we have this factor here called the index of refraction. So let's go to the end of our CAMI for a second and talk about the index of refraction really quickly. Okay. So the index, oops, let's not capitalize everything. And let's actually make this a different color. And let's still not capitalize everything. There we go. The index of refraction formally is equal to the speed of light in a vacuum divided by the speed of light in a medium. Right? But what we're going to say mostly is that that the index, which is called n, is proportional to 1 over the speed of light. Right? So it's inversely related because it's got this definition where the speed of light in the medium is in the denominator. N is inversely proportional. That means that as n goes up, the speed in the medium goes down. Okay, and so you always have to realize that when we're labeling these indices of refraction, as the number gets bigger, we're talking about a slower medium. So air has an index of about 1 because the speed of light in air is very similar to the speed of light in a vacuum. But for example, diamond has an index of refraction of 2.4 because the speed of light in diamond is about 2.4 times slower than it is in air. So let's look back up here and let's take some data going from the more dense to the less dense medium, right? So we're going to go from more dense to less dense. And we'll do this systematically. We'll start at 20 degrees. By the way, I'll just point out that at 0, we're still at 0. So let's go to 10, 20. So let's go to 20. And you can see that the refracted angle, 10, 20, and it looks like about 23. So we'll put that in here. So 20 degrees here gives us about 23 here, even though the first one is 0. Okay, so yay us. So let's try it again. Let's put it at 40. We'll vary it again. So let's see, here's 40 degrees. Whoa, bad. There we go, 40. And so we get 30, 40, and it looks like about 47. Okay, so we'll put that in. Okay, and we'll try it a couple more times. Let's try it at 60. Here's 50, and here's 60. Okay, and at 60, it goes to 60 here, 70 here, 75, and it looks like somewhere right in the middle, so let's call it 77.5. Okay. Right. But let's try at 80 then. So if we go to 80, all of a sudden you see that we have no refracted line at all, right? We have no refracted line at all. We just have reflection. In fact, it changed really close to 60. If I scroll upward, you can see that right above 60, at about 62 degrees, right, all of a sudden I have refraction, but above 62, like let's see, that's 62.5. But if I try to go to 63, all of a sudden it disappears. Okay, so we can say 62.5 is the biggest angle I can make and still have refraction. Okay, so at 80 degrees, right, I have reflection only. Right, I have reflection only because 62.5 degrees, right, is the angle when it refracts about 90, right? And above 90, you're back in the other medium, right? And so we call this angle, we call that 62.5, we call it the critical angle. Okay, that's what we call it. We do. And so that's our critical angle. And so it turns out above 62.5, we only get reflection, and below 62.5, we get refraction, right? And so it is critical. It divides reflection from refraction, which is kind of neat. And we'll talk more about that later. Okay. Either way, you can see that in this system, the angle of incidence, in this case, is always less than the angle of refraction. Right? But again, this is when going from more dense to less dense. Right, so we have to be careful that we specify what direction what we're actually doing in terms of the media. So that means this time we're going from more dense. I don't have a lot of space here. Let's see if I can do this. More dense. Really should have left bigger spaces. To a less dense medium. Right. Then all of a sudden we're going away from the normal line. Right, so it goes opposite. But what the pattern really is that the angle is always bigger in the less dense medium, right? We're going away from the normal line because if we're going to the less dense medium, it's a bigger angle. Okay. Now, mathematically, we can deal with it with an equation that looks like this, but this is ugly and we don't actually have a table of the speeds, but we do have the indices of refraction. And what we're going to do is we're going to use this equation. And this equation is really handy. It's called Snell's law. And often it's written a slightly different way. It's written as n1 over nr equals sine theta r over sine theta I. We're not going to use that a lot. And so in this table here, I'm really going to pretty much ignore this column, and I'm going to ignore this column. Okay. So I apologize, but I'm not really dealing with those. Those two columns are always going to be equal, and you can check this out if you wish. But what I want to do is I want to look at our data. So let's take a look at one of the data points up here. So let's take, for example, we can take 80 degrees and 48 degrees when we were going from air to water. Okay? And if we look at this, we can say, okay, we went from 80 degrees, right? Right, we went to 48 degrees, wasn't it? I think it was. Let's just check to be so I'm not lying to you. 80 to 48, good. And if you recall, I said that the index of refraction in air is just 1, okay? So we need to, and let's see if we can figure out what the index of refraction is here, okay? So when I'm doing something like this, when I'm solving a problem like this, I start by writing my equation, and I'll use my scrap paper down here, and I'll say, okay, let's see what we know. Okay, we know N1, Ni is equal to 1. We don't know Nr, that's a question mark. We do know theta I, right, is equal to 80 degrees. And we do know theta R is equal to 48. So we're going to start this way. We'll say, okay, 1 or sorry, we'll say, write our equation, n1 sine theta 1 equals n2 sine theta 2. So we'll just put everything in. We'll say 1.00 times sine 80 equals our unknown n2 times sine 48. Right? And we can punch this into a calculator if we had a calculator, and I think I do. So let me see if I have a calculator on this bad man whamma jamma. Let's see. Calculator. Here's my calculator. Right? And so I can say sine 80, oh, I guess I have to do sine afterwards, is 0.985. Okay. So if I do that on the left, 1 times 0.985 is 0.985 is going to equal n2 times the sine of 48. So I'll go back to here, and I'll say 48. I'll take the sine of that is 0.743, right, times 0.743. And now to simplify this, I need to divide both sides by 0.743. And that gives me n2 is equal to 0.985 over 0.743. And so let's put that in. 0.985 divided by 0.743 equals, and I get 1.33 because I round, right? 1.33. So that's my answer for this endpoint, 1.33. So I get 1.33. Now, if I look back at this, we said that this was air and this was water, right? And water, right? And if I look at my animation, if I change this to water, right, this is water, then it's 1.33. So I actually have the right index of refraction, so my math works out. Okay, so we can do this with any one of our sets of data, and we can solve for an unknown. Well, we could also do it a different way. Let's try it this way. Let's suppose I take this and I say, okay, well, here's glass and here's water. Let's make this glass for a second. Let me turn off the laser. Let's make this glass, and we'll make this air. Okay, and let's see what angle should it refract at if I aim it at 60 degrees, right? So we'll make the incident angle 60 degrees, and the question is, what angle will it refract at if going from air to glass? Now we see that the indexes of refraction are 1 and 1.5. So if I go back to here, I can write those indices of refraction in. I can say that the first one is 1 because it's still air, and this is 1.5 because this is glass. Okay? The angle I'm going to use for my incident angle is 60 degrees. And the question is, what's this refracted angle? Okay, so let's see. Let's play with it and figure out what it is. So I can say n1, right, is 1, n2 is 1.5, theta I is equal to 60 degrees, and theta 2 is a question mark, right? We don't know that. So we'll say 1 times sine 60 equals 1.5 times sine theta r, right, or theta 2, whichever you prefer, right? So I can do it this way. Well, if I go back to my calculator, I can take the sine of 60, right, and I get 0.866. Right, 1 times 0.866 is 0.866, right, equals 1.5, and I can't do sine theta r because I don't know what theta r is. So I do this. I divide both sides by 1.5, right, and all of a sudden, so let's divide that by 1.5. And I get 0.577. Okay, 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.577. 0.5 and that's sine theta r. But how do I solve for that? Well, it turns out that your calculator can do this, and you just use the inverse button, the inverse sign. So we're going to do what's called sine to the -1 power of 0.577. And I'll show you how to do that on your calculator. If I do that over here, if I go to the second button, I can do second sine, and that gives me the inverse sine button. Okay. Now I wanted it to be the inverse sine of 0.577. I think this is the inverse sine of it, but I'm going to put 0.577, and I'll do second sine. So I get 35.2 degrees. So if I go back here, I should get 35.2 degrees. So I think it's going to be 35.2. And let's test it out over here. So when we turn this on, if it goes through 60 degrees here, right, here's 10, 20, 30, and you can see that our angle is about 35 degrees, and I can't tell that it's 0.2 or not, but it looks like about 35. So it looks like we've gotten the right answer. Okay, so yay us. Okay, so that looks great. Right, so we can do this. So this checks out, and so far so good. Well, there are two more. Let's give you two more problems, and then I'll close up shop, and this will be like 3 days worth of material. Okay, so let's give you two more problems. Let's suppose we have an unknown, right, and we are firing from air. Let's start with air again. And let's suppose we don't know the index of refraction in this unknown media, right? But we know that when we fire at an angle of, say, 40 degrees, right, it gives us an angle of 20 degrees as our refracted angle. Okay, so we'll cut it in half. That's right. That's a pretty big change. So if it does, the question is, what's the index of refraction? So you know everything except N2, and you can set up your equation, N1 sine theta 1 equals N2 sine theta 2, and it will look something like this, right? So you'd have N1 sine theta 1 equals N2 sine theta 2. And if you do that, you can plug and chug, right? And you get 1.00 sine 40 equals N2 sine 20. And so you should be able to solve this and get this unknown here. Okay, but let's actually try a last one. And the last one we're going to do is we're going to try to solve for a critical angle. Okay, so we're going to call this one our critical angle. And this time we're going to have to go from a more dense to a less dense. So let's suppose we're going from glass, say 1.5, okay, to air, which is 1.00. Okay, and we want to find what the critical angle is. Okay, well, we know that we don't know the incident angle that this is going to occur at, and I say the question mark is here. I wrote over here that the question mark was on the refracted side, but it's not. The question is, what's the critical angle, right? The refracted angle for this is going to be 90 degrees. And we know that because when we're above the critical angle, we will get reflection because there's no angle bigger than 90 that will stay in the medium. And below this critical angle, we'll get a refracted angle that's less than 90. So we're looking for this. And so for this last one, you're going to set up your same equation, except you're going to have 1.5 times sine theta critical, right, is going to equal 1 times sine 90, okay? And you can see what the critical angle is. The good thing about this is that when you're done, you can check that critical angle by actually going to here, right? And you can set the incident angle as glass and the refracted angle, or the new medium, as air, right? And you can see that I'm clearly bigger than the critical angle here, okay? So you'll solve for the critical angle, and then you can simply move this around and find where the critical angle is supposed to be, right? You can see it's somewhere between here and here, okay? So that's a quick way of doing it, checking your answer. Yay us, all right? So all you need to do is solve for this and solve for this. Again, you can ignore these two columns. I don't really care about those today, all right? So hopefully that solves some problems. So let's see what we can